All right, very good afternoon to every one of you. It's been a while since we saw last. Without wasting much of our time, let's quickly go to the classroom because we have a lot of questions to cover in this episode. All right, so let's walk down to the classroom and see what we have here. All right, sum to infinity. All right, so please recall the formula we had in the last episode. Okay, episode 5 of this series, where we generated the formula for the sum of a geometric progression. All right, and I told you that both formula are the same thing but existing in different forms. Okay, contrary to what some textbook will tell you or what some teachers will say, that when the common ratio is less than 1, you use this one that 1 is minusing, and when the common ratio is greater than 1, you use this one that r squared n is minusing 1 and all that. But of course, they're just the same thing. They will give you the same answer. You saw that as we demonstrated it in that class, right? Perfect. Okay, so today we're looking at this formula, and so it is from this formula we are going to now adapt it to the sum to infinity formula. What is sum to infinity? When your r raised power n, okay, becomes 0, then of course, for instance, we put 0 here or here, anyone, put 0 here, 1 minus 0 will give us 1, and 1 times a will give us a. That's what we have on top here, then over 1 minus r. So that will give us sum to infinity. How do we come about that? It always occurs when your r is a fraction that is less than 1 and greater than minus 1. All right. For instance, when we have 1 over 10, okay, raised to the power n, where 1 over 10 represents our fraction that is less than 1. Okay, if n is equal to 1, you're going to have 1 over 10 raised to the power 1. And we know that 1 over 10 is something as 0.1. And when you divide, when you raise to the power 1, you're going to have 0.1. Okay, if n is equal to, let's say, 5, you're going to have 1 over 10, okay, raised to power 5. This is what you're going to have. And of course, when you simplify, you're going to have 0.00001. You see, it's already becoming less than, it's already tending towards 0, almost becoming negligible. Similarly, when you have something like maybe 1 over 10, let's say raised to power 10, when you simplify this calculator, you're going to have 0.90. This is what you're going to have. This is almost getting to 0. We are just at n equals to 10. We're not even going to 20, 50, 100, 100,000, 1 million, 1 billion, trillion, and all that. So if even at 10, this thing can be approximated to 0, then what about when it's raised to power 1 million? When it's raised to power 1 billion? When it becomes uncountable infinity. So it's not when I say that when a fraction is raised to power a very large number, okay, very large number, that fraction is approximately equal to 0. All right, when a fraction is less than 1, okay, and also greater than minus 1, is raised to power a very large number, that fraction can be considered to be 0. As you can see, that this is approximately equal to 0. So that is how we come about the formula for the sum to infinity. So let's apply it quickly. Example 1 is find the sum to infinity of the following. So I'll just quickly do number A and you'll do the rest. So our sum to infinity is equals to A over 1 minus R, and our A is the first term, which is 1. What is our common ratio? The second term divided by the first. So 4 over 5 divided by 1, okay, will still give us 4 over 5. Okay, that's our common ratio. So we'll now substitute. Our sum to infinity is equals to A, which is 1, all right, divided by 1 minus 4 over 5. And of course, when you subtract, you're going to have 1 over 5. And finishing up, you're going to have sum to infinity is equals to 5. So this is our sum to infinity. All right. Remember, this is a multiple fraction, so separate them and simplify. Number 2, we are asked, or we are told that an exponential sequence is given by this the sequence. Find the first n terms. Find the first n terms. They did not give us the number of terms, but just say we should find the sum of the n terms, rather, sum of the first n terms. All right, so what do we do for this question? Don't go about trying to generate a nuclear family formula, as I said, all right, nuclear in quote. Don't go about generating a peculiar formula that can only solve for this geometry sequence. You can just use the extended family formula, all right? Those of you who have been following my series will understand what I'm talking about, all right? The formula is applicable to all the GPs, all right? Just use that one then and convert it. Since it's an extended family formula, it will always work for any sequence that is a geometric progression. So when I say our sum, all right, any of the one you remember, which is a into 1 minus r raised to power n divided by 1 minus r. All right, so our first term a is what? Our a is 8. Then our common ratio, we say it is second one divided by the first one. All right, that will give us 1 over 4. So what is our n? Our n is the remaining n. N is equals to n. So we should find the first n term. So now say that implies that Sn, all right, is equals to 8, substituting into 1 minus 1 over 4, 1 over 4 raised to power n, okay, divided by what? 1 minus 1 over 4. All right, so that's what we have. And of course, your denominator, 1 minus 1 over 4 gives us 3 over 4. So we now have 8 into 1 minus 1 over 4 raised to power n, okay, divided by separating multiple fraction 3 over 4. Division becomes multiplication, 1 minus 1 over 4 raised to power n, okay, multiplied by 4 over 3. This is over 1. 8 times 4 is 32 over 3. So we have 32 over 3 multiplying 1 minus 1 over 4 raised to power n. 1 over 4 raised to power n. So this is our nth sum. All right. This is our nth sum. You can also put it in different forms if you want. Question B. What are we asked to find? The sum for large values of n. And of course, you can see our common ratio is less than 1. All right. So large values of n means that when n becomes large, as I demonstrated earlier, you will see that that our common ratio becomes 0. Now see, when n becomes large, all right, when n tends to large value, that implies that our r raised to power n will approximately become 0. We tend to 0. So now see, that implies that sum to infinity is equals to a over 1 minus r. That will give us a is what? 8 from the question over 1 minus r is what? 1 over 4. 1 minus 1 over 4 will give us 3 over 4. So sum to infinity will give us 8 divided by 3 over 4. And you convert, when you simplify, therefore, our sum to infinity will give us what? 32 over what? 3. All right, so that's it. Please confirm for me. All right, let's look at the next question, example 3. In example 3, we are told that the nth term of a GP is 2 raised to the power 1 minus n. The nth term, all right, so we have the nth term. Calculate the sum of the first 4 terms. So we are told that it's a GP, so Tn is equals to 2 raised to the power 1 minus n. Calculate the sum of the first 4 terms. So it means that when n is equals to the first term, n becomes 2, n is 3, and n is 4 is what we are looking for. So we'll just put into this formula and find the first term, second term, and third term. So T1 is going to give us 1 minus 1. If we remove n and put 1, 1 minus 1 is 0. 2 raised to the power 0 is 1. So our first term is 1. Okay, which is equals to a, first term. Then second term is n equals to 2. 1 minus 2 is minus 1. 2 raised to the power minus 1 from indices is 1 over 2. Then our third term, t raised to the power 3, t3 is equals to n minus 3 is minus 2. So 2 raised to the power minus 2 is 1 over 4. And of course, our fourth term, when n is equals to 4, 1 minus 4 is 3. It's minus 3 rather. 1 minus 4 is minus 3. And 2 raised to the power minus 3 give us 1 over 8 from indices. So we have 1 over 8 here. So these are the first 4 terms. That implies the sum now. First 4 terms now give us 1 plus 1 over 2 plus 1 over 4 plus 1 over 8. You can also use the sum formula to find. Now give us, everything will give us about 15 over what now? Please confirm for me. All right, so we have 15 over 8. All right, so that is it there. Then the next question, which is II, we are asked the sum for large positive integral values of n. So n is large. All right, that means it's talking about sum to infinity. Let us confirm if the sum to infinity also, our common ratio should be less than 1. Our common ratio R is, what do we have? T2. Okay, 1 over 2. The second term divided by 1 is equals to half. Half divided by 1 is half. So we are in order. So now say sum to infinity is equals to A over 1 minus R. That will give us A is what? Our first term is 1 divided by 1 minus half. 1 minus half is half. So sum to infinity is equals to 1 divided by 1 over 2. And of course, you can solve to get the answer to be 2. Because when you invert, you are going to have 2 as your final answer. So this is how to solve this particular one. I hope this is simple enough. All right, thank you. Next question, question 4. We are told that the series of the first n terms of a sequence. What is series? Series has to do with sum. All right, series, the sum of the first n terms of a sequence is Sn, this, and find an expression for the nth term. Find an expression for the nth term. Okay, now recall what I explained to us in episode 4. For instance, I want to make an addition of ages, the sum of ages. There are students, the first person enter T1 into the class, the person is 10 years old. All right, second person enter T2, second term, person is 15 years old. When I add the two, I'm going to have sum of the first two, which is now this, as 25 years old. All right, if the next person enter T3, what am I going to do? Let's start from beginning. No, if the third person enter, the person is, let's say, 15 years old. I will not start from beginning to start adding. I will just say T3 plus what? The sum of the first two to give me the S3. So I will not say, so I cannot say that my S3 is equals to the sum of the first two, which I've added before, plus the third person, T3. All right, so this is the relationship that relates term and sum together. All right, to generalize it now, because we cannot do for T4, T5, and all that, we cannot say for Sn, replace 3 with n, equals to, this one is 1 less than 3, so this one is going to also be 1 less than n minus 1, then plus 3 and 3 are the same, so it's going to become Tn. So this is the formula relating them. All right, so if that is, you cannot say from Sn equals to Sn minus 1 plus Tn. Or is that also? So what is our Tn? That implies that our Tn is equals to Sn minus Sn minus 1. So that is our Tn. All right, so that is the formula relating both of them together. Okay, so now what's our Sn? Our Sn was given here, so n into n plus 2 is given. The minus Sn minus 1 is not given, but you can get it from Sn, because Sn minus 1 is just simply replace your n with n minus 1. So wherever you see n, you put n minus 1. This is n. I'm going to have n minus 1. All right. Now multiplying this bracket, that bracket is n plus 2. I'll replace n with n minus 1, n minus 1, then plus 2. So that is Sn minus 1. All right. When we simplify, n times n will give us n squared. N times 2 will give us plus 2n minus, let's simplify this other one first. This is n minus 1, cannot go further. Then multiply by minus 1 plus 2 give us plus 1. So we have n plus 1. All right. If you look at this bracket here, you recognize that it is difference of 2 squared if we are familiar with factorization. you know that is difference of 2 square. Am I correct? Perfect. All right, so if you apply a difference of 2 square now, you are going to discover that you are going to have it as n squared plus 2n minus into n squared, the first one squared, minus the second one squared. And of course, 1 squared is in as 1, so I leave it as 1. Then opening up your bracket, n squared plus 2n is outside, minus times n squared give us minus n squared, and minus times minus will give us plus 1. All right, please take care of that. Many students normally fail that. N squared will cancel minus n squared. What do we have? 2n plus 1. So we now say, therefore, our nth term is equals to 2n plus 1. This is the nth term for the nuclear family. Okay, it's not applicable to other geometric progression. It's just for this particular sequence. We don't know. We're not given the members. All right, so that is what it means. So this relationship between a sequence, the sum of a sequence, and also the nth term of a sequence. All right, so I've explained that previously. Let's move on to the next question quickly because of time. We are told in question 5 that if log x, log y, and log z are consecutive terms, consecutive, they didn't tell us their position. They didn't say it is the first, second, and the third, or it is the fourth, fifth, and sixth. They just say consecutive. All right, so we can just say log x, comma, log y, then log z. All right, so they come one after the other are consecutive terms of a linear sequence. Linear now, not exponential. So common difference we playing here show that x, y, and z are in GP. All right, remember this is log x, log y, and log z. Why they are asking to prove that x and y, not the log, just the ordinary numbers are in geometric progression. So we need to understand what is happening between them. All right, so recall that the formula for a linear sequence cannot solve this problem because we are dealing with x, y, and z, log x, y, and z, and all that. So they are not just pure numbers, so we can't find the common ratios. We don't know the first term and all that. So we just use the principle of AP by saying the common difference, which is this one, this middle one, log y minus log x is equals to another person that is doing log z, okay, minus log y. They will all be the same thing. That's why we say that the common difference is constant. All right, so if you collect like times minus log y will come over and become plus, you're going to have log y, 2 log y, okay, is equals to log x plus log z. I hope you know how I got to log y. When this one come over here, become plus. X plus x is 2x. So log y plus log y is exactly the same thing to give you 2 log y. All right. So we now apply the power law of logarithm. These two will come as a power. We now have it as log y squared is equals to, on our right hand side, we apply the multiplication addition law. They are the same base 10 log xz. All right, by comparison now, okay, this log is equal to this log. That means this y squared must be equal to xz. So now say that implies, by comparison, y squared is equals to xz. What is our y? Y is equals to square root of xz. Now, if you have been following up on this our series, you discover that this is a geometric mean, that the middle, that when you have consecutive terms and the middle one is the square root of the first and the third, then of course they are referred as the geometric mean. So let's say that since y is the geometric mean of x and z, therefore x, y, and z are in GP, they're in geometric progression. So we have answered that question. Is that clear? Any question? All right, thank you very much. No question. Let's look at our last question in this episode. All right, so let's quickly look at our last question for this episode. We are told that the sum of the first 2 terms of an exponential sequence with positive common ratio is 12. So that telling that the common ratio is 12. Of course, that should signal something to you. Positive common ratio. That means you may have 2 answers, and of course, you should use the positive one. Okay. Then if the sum of this sequence, if the sum of this sequence as alright, so if the sum of this sequence as the number of terms increases indefinitely is 16. What is it talking about? If the sum of this sequence as the number of terms increases indefinitely, as the number of terms number increases indefinitely, that means increasing to infinity, find the first three terms of the sequence, the common difference of this linear sequence obtained by taking the log of the terms in question 5i. Alright, so let's quickly answer the first one first before going to question B. So we are told the sum of the first two terms of an exponential sequence with positive arrow terms. So we now have the first two terms. So we have the GPA, all right, AR, that is at the end, then AR square, and so on is the GP, then also. So we now say the sum of the first two is anything as what? A plus AR. The first one plus the second one, AR, is equals to 12. Of course, this will give you question 1 because we are having two unknown variables. So we'll have to find the second equation to complement the two variables, because two equations we will go with two variables. Then the next statement now say as the sum as the sequence goes, the number of terms increases indefinitely. That means talking about sum to infinity. So sum to infinity is equals to A divided by 1 minus R. They say this sum to infinity is 16, equals to 16. All right. And of course, we can say equation 2. Now, from our equation 1, we can factorize our A out from equation 1. If we bring that A out, we're going to have 1 plus R equals to 12. That implies that our A is equals to 12 over 1 plus R. I'll call this equation 1, but modified 1b. So if we now put 1b into equation 2, all right, put 1b into equation 2. What do we have? This is equation 2. So whenever I see A now, I'll put this. So I'm going to say 12, but that will give me multiple fractions. So I will separate it over 1 plus R, okay, is divided by 1 over R. 1 minus R equals to 16. Okay, I separated this division, I wrote it this way. All right. So when we go to the next the next stage, we're going to have 12 divided by 1 plus R. Division become multiplication, and we invert our fraction. This is over 1. So give us multiply by 1 over 1 minus R. 1 over 1 minus R equals to 16. What do we have? Numerator multiply numerator, denominator multiply denominator. We are going to have 12 over 1 plus R multiplied by 1 minus R equals to 16. Now, I left it this way because I already saw something that is unique, which is the difference of two squares I just mentioned not too long ago. When you cross multiply, we are going to have 1 plus R bracket 1 minus R multiplied by 16 equals to 12. 12 times 1 is 12. Then what we have in our next stage, remove this 16 from the difference of two squares. We're going to have 1 plus R bracket 1 minus R equals to 12 over 16. All right. And of course, that will be 12 over 16 as what? 4 go here is 3. And of course, 4 go here is going to give us what? 4. So have it as this. This is difference of two squares. The first one plus the second one. The first one minus the second one. The first one square minus the second one square. So we now have it as 1 square minus R square is equals to 3 over 4. So minus R square come over here, become plus. This one come over here, become minus. So can I say 1 minus 3 over 4 is equals to R square. So what's our R square? Our R is equals to plus or minus square root of 1 minus 3 over 4 give us what? 1 over 4. And therefore R is equals to plus or minus, okay, plus or minus 1 over 2. But we are told from the question that we are using positive common ratio. So we remove the negative one and say, so this when I say therefore that our R, the required common ratio is 1/2, the positive answer. We discard the negative one. Alright, so since we now have our common ratio, what do? We go back to equation 1b to find A. So now say put R into equation 1b. Alright, see 1b here again. That's 1b, 12/1 plus R. So now have our A is equals to 12 divided by 1 plus R, which is now half. And of course, we're going to have it as 12 divided by 3/2. Our A is equals to 12, division become multiplication, 2/3. And what we have, therefore, our A, if we simplify further, we're going to have our A equals to 8. So this is the way we get our A. Alright? Now, what is the question we are asked? Let's go back to the question. We are watching our first term and our common ratio. The question says, find the first 3 terms of the sequence. So we have our common ratio A. Then what is the first term? First term is already A. So we now say our first term T1 is equals to 8, which is A. Okay. Our T2 is equals to AR, which is going to give us 8 times 1/2 common ratio, which will give us 4. Our T3 is equals to AR square, which will give us this one again, 4 multiplied by the common ratio, which will give us 2. So now have it as 8, 4, 2, and so on and so forth. So that is question A. What about question B? What is question B? Question B says the common difference of the linear sequence. The common difference of the linear sequence obtained by taking the logarithm of the terms in 5i. So this is 5i or 5a, anyone? Alright? So this is 5a. Alright, so in 5a, that is question B. Or sorry, in 6a. Alright, so this is in 6a, pardon me. Alright, so that means we are looking for the obtained by taking the logarithm of the terms in 6a. Alright, in 6a. So let's take the logarithm first. So if we now take the logarithm of this number, question B, we are going to have log 8, log 4, and log 2. The common difference now of the logarithm now gives us D is equals to log 4 minus log 8. And of course, which is entire, because you can also do log 2 minus log 4. And when you use your calculator to solve, you can even have it as D is equals to logs of logarithm 4 divided by 8 in base 10. And that will give us log half base 10. And when you simplify finish, you can leave it this way if you want. But if you want to convert finish with your calculating device, your D is approximately equals to minus 3.0. Sorry, minus 0.301. So this is our D. But of course, I prefer leaving my answer this way than all these decimal in exact form. This is exact. Alright, so than this other one. But anyone is your choice actually. Alright, so you can see how we analyze problem, and you can see also the application of sum to infinity. Alright, so it must not always appear as sum to infinity. They can use synonyms. Alright, large values of n and all that, increasing indefinitely. These are synonyms to tell you that okay, it's a very large number, and it occurs when the common ratio is less than 1 and also greater than minus 1. Alright, it could be a fraction less than 1 and also a fraction greater than what? Minus 1. If it is more than 1, if the common ratio is 2, they cannot ask you to sum to infinity. It cannot be using the sum to infinity because, of course, for whole numbers, the more you increase the power, the bigger it becomes. But for any number less than 1, alright, or greater than 0.1, the more you increase the power, the more the number becomes smaller and smaller. Alright, so please take note of that so that you know when to use your sum to infinity. Alright, so this will bring us to the end of this episode. Alright, I will come up with another episode whereby we're going to look at combined AP and GP, how to see how questions can combine AP and GP, and of course we also see the application of AP and GP in real life problems. All right. So please still follow up on this series of this sequence and series you'll be considering, and of course do recommend this video if you have learned something today. If this video has been helpful to you, please do recommend it to somebody else that is also looking for a resource material to enhance his understanding in mathematics. And it's also useful for people preparing for examinations, especially our senior high school students who are preparing for their West African examination. All right. And finally, one of the benefits of this video is that you can always rewind, pause the video, and to understand whatever concept you are missing. Okay, so that is one advantage of this. Thank you very much. We'll see you in the next episode. But before you go, here is your practice question. All right, so that's the practice question. Please do not forget to subscribe to this video, to this channel if you have not. Thank you. It is a goodbye from me. We'll see in next episode.